Good morning, everyone. So I'm Andrea Bartolini. I'm assistant professor at University of Bologna, and today I'm here to present our work on combining out-of-band monitoring with AI and big data for data center automation in OpenPOWER. So during this presentation, I will start by presenting you the concept of data center automation, what it stands for, and what its aim. Then I will go through the work that we have done on the Davide system, OpenPOWER system, located in Bologna, so 1 petaflop system for improving out-of-band monitoring, and also combine it with big data technology for supporting the data center itself monitoring. Then I will go through the solution and the approach that we take toward combining big data and AI for anomaly detection and center automation in this purpose, and then I will briefly discuss our future works and direction. So, what is data center automation? So in this picture, what I depict is the fact that you have a data center in which you have several clusters and racks. All of them have sensors, have information that can be collected. Then in the same room, you have a crack, cooling system, PDU, and environmental sensors. So what you need in order to automate your data center, you can leverage all these sensors to create an infrastructure in which all this information are fed through this an ecosystem on softwares which allows you to actually learn, extract information from the data center itself, and combine them with machine learning tools, performance analytics tools, and data visualization in order to improve the efficiency of the systems, where the target is indeed trying to improve its energy efficiency, but also the usage of the resources and the performance of the system itself. The use case scenario that we envision for data center automation two of them are depicted here. We have on the left, we have the case in which we have our computing nodes with its own internal components. We have CPU, accelerator, GPU, and we have a normal user, the blue and the red, which run application on the hardware. Then we have malintentionate users which may attack the system. We have components, mechanical components, which may have faults, which can degrade their performance, and we have the monitoring tools that are depicted here. So standard tools for monitoring the system are coarse-grained, in the sense that they do monitor things, events which happens really with not high frequency, and so you are really not too much capable of discriminating the different events and things which happens. Whereas with fine-grained monitoring, what you aim for is to have a higher resolution on the telemetry of the system, which allows you to be capable of discriminating things, so separating events and effects on the system. And the purpose of this is that to then enable actually the capability of being capable of evaluating if your computing nodes is in spec or out of spec, if it's misconfigured, or if it's aging and wearing out, and also enable predictive maintenance. On the other side, you have instead another usage scenario for data center automation, which is the fact in which you have a data center, you have several users which submit jobs and use your system, and then you have physical constraints which come from environmentals, which are actually maybe the fact that you want to operate the system under a specific power envelope. So you want to, among time, be capable of operating your entire data center within a specific total power budget, which may change in times, and maybe this can happen due to the fact that you have transition installations in your data center. So you have that you need to shift the power budget to a new system which is coming. You may have grid service level agreement, which tells you that you cannot consume a higher amount of power than if there are some natural disaster or some shortage of green energy, you need to reduce your total power consumption. And what you want to do is that trying to have the highest service level on your data center. So you want to actually maximize your productivity within these constraints which are happening. So you need automated tool for supporting this decision. It cannot be just a system administrator that changes things in your infrastructure, because it cannot cope with all these complex constraints. And similarly, if you want to actually verify if your large-scale system, if you have a misconfiguration, if you have things which are wearing out, you cannot just provide simple visualization, because because it will take time, a lot of time. It's actually taking time and a lot of effort, economical effort in data center system to actually be capable to to look at the traces that you are monitoring if you have a lot of data and be capable to extract useful information from that. You spend a lot of time as system administrator in digging through a ticket from a user that tells you that, okay, my job wasn't running as expected. Then you have to dig down, discover if was the job which was compiled not in the proper way, or was the hardware that was out of spec. It was a misconfiguration in the node that when I have updated the firmware in all my nodes, one node was not really responsive in the network and was staying at the old firmware. So you don't really get all these things, and you want to do it in an automated fashion. So if we do a data center automation based on the monitoring system, I said before, our components are, we have the nodes, we have the infrastructure components in the system, and then we do collect all the information and we send it to a centralized mind, which is collecting all the data and doing analytics. Okay, nice, good. However, we have bottlenecks. As the system scaled in terms of scale of the system, and if you start to even increase the frequency at which you monitor events, you will suddenly ended up in having problems in collecting all the data. You kind of have overhead in the bandwidth to collect all the data, and then you start to have software overheads in collecting this data from the computing resources. A different approach will be to actually leverage edge computing. In some sense, you can actually try to add computational resources to your node that are capable just to take care of a small computation that is the algorithm that you train on the largest amount of data, and then try to actually distribute them to the process to the node itself to actually actually communicate to the centralized entity the events. So if you are misconfigured, or if you are aging out, so you need to transfer the knowledge down to the compute node itself without harming their own performance. So let's see how we do it on the Davide system. So the Davide system is a system that has been installed last year in Cineca in Italy, has been ranked in top 500 in 500. It's an OpenPOWER system. It is based on the IBM MISC system. It has two Power 8 sockets, and for NVIDIA P100 system, it is liquid cooled, and it has an additional board component that has been designed in University of Bologna in collaboration with the TH Zurich to actually improve the self-awareness of the node and to enable fine-grained power and performance monitoring and analytics on the node itself. This component, this out-of-band component, is actually an embedded system which is connected to the node itself. So we have added one of the system in each of the nodes, and it serves for several purposes. So it's a power measuring block. So it's high frequency power measurement on the node itself. It is based on an embedded system, an embedded system which is capable to do additional tasks on top of the one that's just monitoring the power, such as also connecting to all the performance metrics which are within the nodes and collecting them. It does support scalable communication interfaces such as the MQTT protocol that we'll see later, and it also supports to offload some of the analytics directly on the edge on this small system to actually process the data which are collected and just generate events based on, let's say, based on be capable of actually understanding if you have anomalies which are going on. The system is actually, looking at the fine-grained performance, is pretty unique. So it's capable of sampling the power consumption at 50 kilohertz per second. So we have 50 kilohertz, so 50 kilo sample per second of the power consumption with high accuracy, so sub precision, and with supporting time synchronous protocols, so NTP and PTP. So we can have that actually all the nodes of the cluster, we can actually align all the power consumption readings between all the nodes of the system. So we can actually have a kind of a live oscilloscope for the entire cluster. And it's better with compared to state-of-the-art monitoring system of competitive product. Okay, but nice. What do we do with this high-frequency power monitoring? So First insight of what we can gain by actually using high frequency power monitoring is the fact that now we can actually do a lively spectral analysis of the power consumption, and we can actually discriminate application which runs on the different application which runs on the node by looking at their spectral components. So we actually have signatures of the application which are running on the system. This is actually an interesting feature because if one of the two applications is the normal application and the other is an attacker, we can actually have a lightweight intrusion detection system for each of the node, which can actually enable the detection of unwanted usage of the compute node. So this can be an additional actually way of checking if the system is doing what is expected to do. Okay, but okay, now you can compute an FFT on the power trace that you can monitor lively on the system, but can I automate all this behavior? So that goes to combining big data and AI enabled automated anomaly detection on the system. This is done through the monitoring framework that we added to the Davide system, which is an open source project of the University of Bologna, which is called Hexamon, which is actually combining MQTT streams of sensors, which with scalable big data technologies such as we have Cassandra databases, Kairos DB time traces, and then connecting on top of these components, we connect actually AI tools such as Spark, Kafka, TensorFlow to actually do automated analytics on this data. So we have the each of the sensor location is publishing data, and then we have capability of have a kind of flexible and scalable storage of this data for creating data sets based on the live vital signs of the data center, and then do analytics on top of that. MQTT is a good tool for propagating telemetry data because it's really lightweight in terms of the protocols, and it allows really to create communication channels which are effective in the system. So how we do it in Hexamon is basically we have different sensors, these different collectors of data positioned along the system, and then we have data brokers which collect the information in communication channels, and these are actually inserted in table in the Cassandra databases that then can be used later for enable automation on the system. If we look at how we configure it on Davide, we have that all the node has its own embedded system monitoring board, which is based on the Big Robot Black platform, and is collecting data, both high-frequency power data and also telemetry sensor data. And these are propagated to a database which runs on a management node, and together with the data of the computing node, we also have Slurm, so the job scheduler, which also propagates events. So if a job is starting, has been the request of the jobs, and insert this in the database. And also we also collect data coming from the IPMI sensors and also from the cooling system. So we have an holistic collection of data in a central point, which allows to correlate between different things which are happening. And then we can, based on that, we can create we can use this source of data for analytics. This we can do actually by combining the data sources with Pandas data frame, and then enable with also Spark, PyTorch, TensorFlow, and Kafka tools to analyze the data that we have collected, to create actually an entire framework for anomaly detection. So that's coming to the next slide. So how is working? So we have different nodes which have additional components which are capable of collecting all the information with high frequency that are telemetry data of the computing nodes. This goes to the monitoring infrastructure that I just described before, and all this information are collected. Then we have the capability of keeping a small buffer of high frequency data and to create some historical traces. And based on these historical traces, we do train deep learning models for actually which represents the data which we have collected. Then once we have trained the model, we can offload the model that we have directly on this component that we have to the nodes, which can actually run the inference of based on the live data which are collected, and actually understand if the node is behaving normally or if it's under an anomaly. Does it work? So we have implemented it on Davide. So we used as a component for doing anomaly detection, we started with the simplest tool, which is an autoencoder. So an autoencoder is nice because it's enable you to have a set of features and recreate the representation of this feature by actually trying to understand the correlation between these features. And if you train if you use an autoencoder, you are capable basically of having of trying to estimate based on the feature the same features. And if your representation, so if your model is good, you are actually capturing the behavior of the system. And this you can do it without knowing the physics and the laws which combines all the sensors, so it's done automatically by the tool. So the idea is that an autoencoder is capable to recreate unseen input, relation between unseen inputs, and so if is capable of recreating the unseen inputs if these one are actually behaving correctly, but if this is not going to be capable of actually recreate the inputs if the system is not behave in the proper condition as it has been trained. So basically the idea is that to train autoencoder with the normal behavior of an high performance computing system and to reconstruct and to use the reconstruction error to detect if there is an anomalies. In fact, so when you try to build an anomaly detection system in an HPC system, the problem that you usually have is the fact that you have a lot of data of the normal behaviors, but you don't have a lot of data on the anomalies because the anomalies that are happening are really faults that happen in the system, so they're really sparse in time, and so you don't collect them at all. So the idea is that you can create models of the normal behaviors that will tell you then when you are out of the normal behaviors, and then you use this information to detect if the system is behaving correctly or not. So how we did it? So basically we create a really simple autoencoder with just 3 layers, and we train it on 2 months of normal data of Davide. So we just have all this our infrastructure. We just have 2 months of normal behavior of the Davide nodes, and we train a model which is capable actually to tell it is to understand the correlation between the sensors, to create a model of the understanding of the sensors. Then how do we validate? We validate by artificially inject anomalies on the nodes. And these anomalies are actually can be of different sources. In this presentation, I'm focused with anomalies which are actually misconfiguration of the node. So in which I actually, by artificially have misconfigured the node, such as I have placed different power governors in my operating system, or if there is a problem in the system, such as and the power governor cannot work. So I have 2 anomalies which are 2 different settings. And I'm trying to apply the anomaly detection algorithm, so my autoencoders, if it can actually detect it. So in a live system, so these are unseen data for the system I have for my computing nodes. I'm looking at the residual, so the capability of the model to actually predict the real input traces. And if the system is behaving correctly, I have really low residual in my algorithm, but if I have injecting faults, I can see that actually the model is no more capable of representing the truth of the system because the system is behaving differently, and I can easily recognize that the system is behaving not in the proper conditions. So I can have an automatic flag for anomalies which are happening in the system. So it's behaving good, so we tested in several nodes of Davide, so we have a good prediction of the normal and anomaly behaviors, and we can also move this computation, so the inference within the embedded computers that we have on each of the nodes, so we can actually execute easily with the TensorFlow on the big on black the inference with 11 milliseconds, so we can actually do it lively on the system. We can actually use MQTT to just propagate if the system is behaving normally, or if it is misconfigured. So this actually proof that it's possible to use a scalable monitoring system powered by and the out-of-band monitoring system of the OpenPOWER system to actually create automated way of of data center automation, so actually to automate the work of system administrator in checking if the node is configured properly or not. And this is just the beginning, so we are working actually in trying to improve this technique. So we are working in so we actually, in conclusion, what we have done, we've presented that an approach which combine out-of-band monitoring, big data, and AI to enable data center automation. We prove that our approach is capable of enable automated anomaly detection on computing nodes. And we are actually working on extending this approach towards security, so try to see if we can use this approach to detect bad usage of the system, not allowed usage to the system. Also to see if we can actually automate housekeeping tasks in the data centers. And then we are exploring to take advantage of the OpenBMC community to see if we can move part of this solution to the close by to the computing node, and also looking for open hardware to see if we can improve the efficiency of the solution. And we are looking, of course, for partnership to bring this solution in Power 9 systems. So this concludes my talks. If you have questions, I'm here. This is the team, so I acknowledge to the team that's working with me in this topic. Thank you.